All right, so I guess I'm live right now. So hello, and welcome everybody on this beautiful platform of PW. This is your physics mentor Gaurav Tiwari. And today, my dear kids, we'll be having a discussion of chapter called thermal physics, and then we will be discussing oscillation and waves, right? So before we start with anything, just clearly let me know, first of all, let me know if I'm clearly audible or and visible or not. Hello, Ananyam. Kaise ho bhai? So we'll be discussing some questions from the chapter of thermal physics and oscillation waves. So nearly 50 questions will be there. All the questions I have picked from previous year questions, right? So these are the questions that you will be solving anyway, right? But I'll give you a trend, right? What are the types of questions that are asked in recent years, right? So that is where we are going to focus. So in thermal physics, we'll be talking about questions from, basic thermal properties of matter. Some questions I have picked from there as well. And then thermodynamics. And then we will be talking about kinetic theory of gases. So 3 chapters are there in the first part. And then in the second part, there are oscillation and waves. So some questions are there in this part. So around 30 questions will be from thermal physics. Around 20 questions will be from oscillation and waves, right? So 50 questions in total we have in this particular lecture, right? So without any further delay, let us start talking about this particular session, right? And as always, first of all, I'll be giving you some questions to solve, right? I'll be showing you the question, right? I'll explain you the concept mostly, and then I will give you the time meanwhile, so you can solve it while I'm explaining the concept. If you know it, you can solve it, right, along with the lecture, right? So the best way to attend it is just pick up your pen and paper and solve it with me, right? The best way to attend this lecture is because it has 50 previous year problems and selected problems, right? So pick up your pen and paper, and you will find that similar kind of problems will be asked in the NEET exam, because that this is where the trend is going, right? Okay, so just speculation, I would say. So the thermal physics is there, the part 1. Let's start with the first question. So this is the first question of thermal physics. It says that a metallic bar of Young's modulus 0.5 10 to the power 11 Newton per meter square and coefficient of linear thermal expansion 10 to the power -5 per degree centigrade. So alpha is given. Length is given 1 meter and area of cross section of that bar is 10 to the power -3 meter square. That is heated. This rod is heated from 0 degree to 100 degree without expansion or bending. The compressive force developed in this one is, right? So it's a good question. I have picked this question in one more lecture, but it's a very good question, I would say, right? Okay. So it's a really good question, I would say. So just have a look into this one, right? It's a good question, I would say. And it is asked in the year 2024. So very recent trend is there in this question, right? So Surya and Epi and all everybody. So let's talk about that. So meanwhile, if you can solve it, I'm starting the time for you, right? So I'm starting a time for a minute for you, right? So you have a minute and you can start solving. For those who cannot solve, I'm giving you the hint and the concept behind it, right? So this is where the things go. Okay. All right. So you can take your minute and solve it. So the concept of this question is as follows, right? So here we are saying we are heating a rod, a metal rod, and it is not expanding, right? So think about it. Ideally, if the rod was free to expand and you are heating it up, it will expand. You cannot stop it. It is bound to happen, right? But we have created conditions, and in those conditions, the rod is heated without expansion. That means we are stopping it from expansion. That means at this end and in this end, we are providing a stopper, right? So basically, the rod cannot go beyond these means, right? Beyond these ends, right? And when you are heating it up, what will happen? The rod will try to expand. And when the rod is expanding, but the place is limited, so what will happen? The rod will push against the supports, right? The rod will push against the support. You are not allowing it to expand. Here, you see that? You are heating from 0 to 100 without expansion or bending, right? So what will happen? When you are heating, it is pressing against the support. So what will happen? These supports will apply the reaction force on the rod, and due to the reaction force, the rod will be under compression, right? Due to the reaction force, the rod is trying to expand, right? And it is pushing against the walls. But what is happening? The wall is not allowing it to further expand. So what is happening? It is producing the compressive stress in it. We have to talk about that compressive stress, right? So the idea should be very, very clear. Done and dusted. Very nice. Okay, so let's have a look at that. So the idea is this is the basic concept behind it, right? So that's how the compressive stresses are created. Now, you know that how much force will be created? You see that the force created due to the expansion is going to be alpha delta T into Young's modulus. YA alpha delta T. This is going to be the force that will be created, right? So my dear kids, we can say that the value of force is YA alpha delta T. If some kids do not remember this formula, I will tell you a little way out for that as well, right? My dear kids, some kids remember that due to the thermal expansion, when you heat things up, the thermal expansion they remember is delta L, right? And they remember that delta L is alpha delta T, right? Delta L is alpha delta T, right? So this is the expansion per unit length. It is alpha delta T. My dear kids, this is the delta L upon L, you can say, expansion per unit length, alpha delta T. My dear kids, you can also call it thermal strain. What you can call it? You can call it thermal strain, right? So if you have a metal with expansion coefficient alpha and you are heating it for a temperature difference delta T, the thermal strain in that will be alpha delta T, my dear kids, right? This part is something that you know, right? And now you know that thermal stress upon thermal strain, right, is equals to the Young's modulus of that material, right? So what will be the thermal stress? We can say that whatever force is being created, expansion force per unit cross-sectional area, that is the stress. So, and what is thermal strain? This delta L upon L that you have seen over here, delta L upon L, right? My dear kids, we know all the values, right? So what is the stress over here? So F upon A, right? And put the value of strain directly. Strain is alpha delta T, and this is equals to the Young's modulus, my dear kids, right? So what will be the expansion force? This force is something that is created due to the heating process, right? So YA alpha delta T. I believe the idea is very, very clear, right? So when you heat up a metal piece of thermal coefficient alpha by the temperature difference delta T, my dear kids, then the force which is created, the expansion force which is created is YA alpha delta T, and we have used that formula over here. So the concept is clear, I believe, with everybody, right? Okay, and when you use all the values given to you, Y, A and alpha, everything is given, the force, the compressive force will be calculated. Okay, so 15 10 to the power 3, which is the option number B, right? So let's see that how many of you gave the correct answer, right? So in the previous question, the fastest answer was given by Surya, and then the answer was given by Ananya. So Surya and Ananya gave the fastest answer, right? So let's move on and talk about the next one, right? Okay. Right, so the next question is, again, if you can solve it, I will give you the time, you can solve it directly. A copper rod of 88 centimeter and an aluminium rod of unknown length have their increase in length, which is independent of increase in temperature, right? Independent of increase in temperature. The length of aluminium rod is, what will be the length of aluminium rod? So it is asked in the previous 10 years. So I have tried to select maximum recent questions, right, that have some concepts in them, right? So now what is happening? We have a copper rod, it has a length of 88 centimeter. We have an aluminium rod and we don't know the original length of the aluminium rod. They have their increase in length, which is independent of increase in the temperature. That length of the aluminium rod is going to be, so alpha for aluminium and alpha for copper, both of them are given over here. So again, you have your minute to solve, right? Just take a minute and try to solve it. Okay, take a minute and try to solve it, my dear kids, right? It's a very good question, right? Okay, so it is independent of temperature. That means the temperature difference is same for all of them, and it will be cancelled out in both sides, right? Okay. So my dear kids, for those who cannot solve it, I am giving you the conceptual hint first of all. So the concept over here is this, right? So in the question they are giving us that in this one and this rod, what is really happening? The increase in length is same, right? The increase in length that is happening is same in both of them, right? So what is really happening? The change in length, if the original length is L, right, you know that delta L upon L, deformation per unit length due to the thermal stress, is basically thermal strain. Delta L upon L is alpha delta T. So the total deformation is going to be alpha delta T into L. I hope the idea is very, very clear. The total deformation is going to be alpha delta T into original length. My dear kids, we have a copper rod and we have an aluminium rod. So we can equate these two things for both of them. So we can write down alpha copper right? Delta T is same for both of them because this deformation is independent of temperature. So we will write delta T, and L is length of copper rod. Okay. And the same things we can write for the aluminium rod. All right. So alpha for aluminium, delta T and length for aluminium rod, right? So you see that delta T is cancelled out from both sides. So what is going to happen? Alpha for copper and alpha for aluminium is going to be length of aluminium upon length of copper rod. So you see that everything is here already available to you, right? Alpha of copper is given this, alpha of aluminium is given this, length of aluminium is something that we have to find out, and length of copper is 88 centimeter. So this is the ratio, length upon length. So you don't have to convert centimeter to anything else because that will anyway cancelled out. So now from here you have only one variable, which is length of aluminium rod. You can figure out, right? So I hope the idea is very, very clear. Surya has given the answer. Let's see that how many kids have given the correct answer, right? Okay. So the value, the final value is over here, right, which is 68 centimeter. So which comes out to be option A, right? So the concept I have already explained, and let's see that option A. And here you see Surya and Ananya again gave the correct answer. Very nice. So let's move on and talk about the next one, right? Let's move on and talk about the next one. So here we have a question from the previous year, like 2025, right? So these kind of questions are in the recent trend, right? So practice them efficiently, and you have to practice them. You cannot avoid them. So there are this question: 3 identical heat conducting rods. They are connected in series as shown in the figure. So there are 3 identical rods. They are connected in series as shown in the figure. The rods on the sides have thermal conductivity 2K. So this rod and this rod on the sides, they have thermal conductivity 2K, right? And that in the middle has thermal conductivity K. Okay, so this one and this one has thermal conductivity 2K, this one has K. The left end of the combination is maintained at temperature 3T. So left end of the combination is maintained at temperature 3T, and the right end is maintained at temperature T. So this end is maintained at temperature T, right? The rods are thermally insulated from outside. So this rod is thermally insulated from outside, okay? In a steady state, what is going to happen? The temperature at the left junction is T1. This is the left junction where two things are meeting. This is the junction. The temperature at the left junction is T1. At the right junction is T2, right? So what will be the ratio of T1 upon T2? So again, a very easy question, right? Simple formulas for a steady state you can apply. And again, I will be explaining you the concept. You have 60 seconds. Those who can solve it should start solving right away. But those who cannot solve it, I am explaining you the concept. Then I will show you how to solve it, right? So the concept is over here. For those kids who cannot solve it, right, they can start looking at this particular thing, right? So this is going to be the conceptual part, okay? Right. So over here, what is really happening? We have this end and this end. And in between these end, we have 3 metal pieces, 1, 2, and 3. And all 3 of them have same length, L, 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 right? So because they are given 3 identical heat conducting rods, that means they have the same cross-sectional area and same length. That is why they are identical, right? And this one has thermal conducting coefficient is K, this one has K, right? And length is LLL, and this is T1, this is 3T, this is T, and this is T2, right? So these are the variables given in the question, right? My dear kids, now what is really happening? At a steady state, we can say the rate of heat transfer through this junction is same as through this junction, right? At a steady state, we are going to have the same rate of heat transfer across the junctions, right? So what is really happening at this junction? Think about it. What is really happening at this junction? So we can say here we have temperature 3T, right? So if we know we have a metal piece, we have a temperature here and here, we know the temperature across these ends. So we can say the difference of temperature will decide how fast the heat will transfer across this one. So we can say that here the temperature is 3T and on this end the temperature is T1. So what will be the rate of heat transfer through conduction? We can say that it will be K. Thermal coefficient over here is 2K. Cross-sectional area, let us say, same for everybody, and it is A, right? So Ka delta T. What is delta T over here? We can say that 3T minus T1. 3T minus T1, right? Upon 2Ka delta T, 3T, the temperature over here is 3T, the temperature over here is T1 upon the length, the distance between these two ends is this, right? So this is how fast the heat is conducting from one end to the other end, right? Now think about it. This is at the steady state. So same things we can say about this other junction as well, right? The same things you can say about the other junction as well across this one. At the rate at which this heat is transferring to this one, the same rate the heat will transfer to this one as well, because we have acquired the steady state. So what is happening in the second part? So we can say that in this one, the thermal conducting coefficient is K. This is T1 minus T2, area is A, T1 minus T2 upon length is again L, right? Length is again L, right? So from here, you will get a relation between T1 and T2. From here, you will get a relation between T1 and T2. My dear kids, at a steady state, the same thing will happen between this and this pair as well, right? Between these two pair as well. And again, when you do that, right, and make another equation between these two parts, here you have made an equation by considering the first two parts. This is the equation. You can consider the second two parts and make another equation of T1, T2 and get the values that you need, right? You can get the required ratio, right? I hope the concept is very, very clear. This is the conceptual understanding across this. At a steady state, the rate of heat flow is going to be same during the conduction process. So here is the solution, you can say. So you have applied the same across this junction. You can say that when you are equating them, so you see that the same stuff you have done and you got one equation between T1 and T2, right? This is the first step. In the second step, you consider the second and third part, right? So T1 minus T2 into K, right, or Ka T1 minus T2 upon L, right? This is for the first part, which is written here, Ka T1 minus T2 upon L. And now go for the third one, 2K into A T2 minus T upon L, 2K into A T2 minus T upon L, right? This is what you have done. So again, you will have another equation between T1 and T2. So this is the first equation between T1 T2. This is the second equation between T1 and T2. Now you need to know the ratio. So you can easily get the ratio, which is 5:3, right? So 5:3 is the ratio that you're going to get. So option A is correct, okay? And in this one, the fastest answer was given by Ananya this time, right? Okay. So keep on answering, right? Every kid should answer, right? So let's keep on moving and talk about the next part. The mechanical, again, from the NEET 2023, again a recent year question. The mechanical quantity which has dimensions of reciprocal of m inverse is, so this is from the chapter 1, you can say. You need to know the formula for these things, angular momentum formula and all those things you need to know. And based on that, you can write on the dimensional formula. So nothing much to discuss about this over here. But just for the sake of it, you need to know these, questions, right? Like you need to know these units, right? Because torque you already know from other chapters, gravitational constant you other know from gravitation, angular momentum you already know, right? But from this chapter you have to pick the thermal conductivity. By the previous formula you can take, right, thermal conductivity, and from there you can calculate its unit, okay? All right, so K ka unit ye hai, okay? So now here you can talk about this idea, the energy that will be ideally radiated by a 100 kilowatt transmitter in 1 hour. Again, energy transfer, heat transfer is a very important topic again. So from 2022, this question is there. The energy that will be ideally radiated by a 100 kilowatt transmitted in 1 hour. 100 kilowatt transmitter you have, and how much energy will be radiated by that transmitter in 1 hour. So it's a very basic question, right? It's a very basic question. Those who know can solve it, and those who don't know, I am telling you the concept, right? Okay. Over here, this is the concept, right? Okay. We have to tell the energy that is radiated. So my dear kids, what is energy? We can say energy is the rate at which the work is done, right? The rate at which the work is done. So here we have 100 kilowatts. 100 kilowatts mean, right? Kilo means 10 to the power 3. That means 100 into 10 to the power 3 watts, right? That many watts. And what do you mean by this thing? This unit, watt is joule per second, right? So this is radiating 100 kilowatt. That means 100,000, right? 10 to the power 5 joules per second, right? 10 to the power 5 joule energy is emitted every single second, right? We have to answer how much energy will be emitted in 1 hour, right? How much energy will be emitted in 1 hour? So we can say in 1 second 10 to the power 5 joules. So in 1 hour, 3600 seconds are there. right? 60 into 60 into 10 to the power 5, that many joules will be coming out every hour, right? I hope the idea is very, very clear. So just multiply it. So you have 36 into 10 to the power, these zeros will add up into 7, right? So option A will become the correct option, right? Option A will become the correct answer. Yes, Bhuvneshwar. Okay. We'll talk about that, Bhuvneshwar, right? I cannot reveal everything over here, but yeah, you will see soon get the idea, right? So over here we have very clear idea that Surya gave the correct answer for this one. Okay. So let's move on and talk about the next one, right? So the power radiated by the black body is P and it radiates maximum energy at the wavelength lambda naught, right? So again, the power is radiated at the energy wavelength lambda naught. If the temperature of the black body is now changed so that it radiates maximum energy at wavelength 3/4 of lambda naught, the power radiated by it becomes N into P. What will be the value of N? What will be the value of N? Again, you can try. Right, you can keep on trying for this particular problem, slightly lengthier problem. So I'm giving you 90 seconds, right? And for those, again, those who can solve it, they can solve it right away. And for those who cannot solve it, I'll be giving you the hints so that you can solve it, right? So my dear kids, what is really happening? The power radiated by the black body is P, right? And it radiates maximum energy at this wavelength, right? So wavelength corresponding to maximum energy, right? How do you relate that? We can say that we can relate it by Wien's displacement law, right? The energy the wavelength corresponding to maximum energy is lambda max, right? And we know that at a temperature T, the product of lambda max into T is a constant, right? We understand from there that if the temperature rises, the lambda max, the maximum wavelength, shifts towards the left. That means it reduces, right? So, but the product of these two things is constant. We have written the Wien's displacement law in this way, that the maximum wavelength is inversely proportional to temperature, right? Maximum wavelength is inversely proportional to temperature, or lambda max into T is a constant. This is the Wien's displacement law, right? This is the concept which is going to be applied over here. The question is saying that initially the black body is emitting the power radiated is P, and the maximum energy radiated at wavelength lambda naught. If the temperature of the black body is now changed so that it radiates maximum energy at 3/4 of lambda naught, so clearly the wavelength has reduced, the temperature might have increased, right? Now the maximum wavelength is lesser than the previous one, 3/4 of lambda naught, so clearly the temperature is increased, right? So the power radiated by it becomes N times the previous power P, right? The value of N is, what is the value of N? So clearly we can talk about that. Now, this is the first set of concept you will be applying in this part. The second concept you can think of is how much power a black body radiates, right? From the Stephen Boltzmann law, I believe you know that. From the Stephen Boltzmann law, you can say that the power radiated, right? Power radiated is proportional to 4th power of temperature, right? This is the Wien's displacement law, and this is the Stephen Boltzmann law, right? So this is the second concept that you need to know. From Stephen Boltzmann law, the power radiated is by the black body is proportional to 4th power of its own temperature. So the hotter the body, the more power it's going to radiate. So clearly, it is now at a higher temperature because lambda max has now been reduced 3/4 of previous value, right? So lambda max is reducing. That means the temperature will rise, right? Because of the temperature has risen, the power will also become certain times of previous value, right? Higher than the previous value, right? So now I believe the concepts are really, really clear, right? What are the concepts we need to apply over here, right? And now we can go ahead and try to solve it, okay? Right. Yes, Ananya. So let's move on and talk about the next one. So here we have it. So here you can say that in the previous value, when the wavelength was lambda naught, and now the new wavelength is 3 lambda naught upon 4, right? The product is constant, lambda max into T is constant. So lambda max into T in the previous condition, and when you have changed it, these are going to be the same, right? So when you equate them, you can get the ratio of T dash upon T, which is this, right? Okay, the new temperature is 4/3 times of old temperature T, right? Okay. And now you know that power emitted is proportional to fourth power, right, of temperature. So you just take the ratio. P dash upon P is going to be T dash upon T to the power 4, and N becomes 4 by 3 to the power 4, right? So this is how you can get it, which is 256 upon 81, and you can correct the answer, 256 upon 81, right? So this is how you can go about it. Just you have to apply the concept, right? So my dear kids, I want you to focus, right? And here you can understand that mostly the questions involve a single concept, right? Some good questions involve two concepts. That's it. This is how far the NEET goes with you, right? That's it. Okay. So you have to be very clear about that particular part, right? Let's move on and talk about one more thing. Okay. So here what is happening, we have two rods, rod A and rod B of different materials. They are welded together as shown in the figure. Their thermal conductivities are K1 and K2. The thermal conductivity of the composite rod will be, so what will be the thermal conductivity of the composite rod? So it's a direct formula, right? I guess I don't have to solve in this particular question. So in the previous question, what was the answer? C. Okay. So Ananya was the correct kid in the previous question as well. So solve this one, right? So here what is happening, we have two rods added like this, right? Okay, so we have to talk about what will be the effective thermal conductivity of the entire combination, right? So it's a direct formula. Okay, it's a direct formula, right? Effective thermal conductivity in the parallel combination. What is the effective thermal conductivity? We can say that if this one has cross sectional area A, right, this one has cross sectional area A, this one has cross sectional area again A2, let's say. First one has A1, second one has A2. So we can say K1 A1 upon K2 A2, K1 A1 plus K2 A2 upon K1 plus K2, A1 plus A2. K1 A1 plus K2 A2 upon A1 plus A2. That will be the effective thermal conductivity. It's a direct formula, you can say, right? K1 A1 plus K2 A2 upon A1 plus A2, right? All right. And since these rods have same cross sectional area, right? Same cross sectional area. So A1 and A2 must be cancelling out because, yeah, right. So K1 and A1 and A2 cancel out, it will become K1 plus K2 by 2. Okay. So option D is the correct option. Okay. Option D is the correct option. Okay, I forgot to start the poll for this one, but option D is the correct option. And in the chat, Ananya gave the correct answer, and Surya, okay, Surya is also very correct. Okay, let's move on and talk about the next one. So the next one is two metal rods, 1 and 2 of same length, have same temperature difference between their ends. Two metal rod, first metal rod and second metal rod. First metal rod has a temperature difference T1, second metal rod has a temperature difference T2. Their thermal conductivities are K1 and K2, and cross-sectional areas are A1 and A2 respectively. If the rate of heat conduction in the first rod is 4 times in the second, then what will be the correct relation between K and A, right? What will be the correct relation between K and A? Okay. So what is really happening? Heat conduction is happening, right? And rate of heat conduction is 4 times. The rate of heat conduction in the first is 4 times in the second, right? So idea is going to be very, very simple. First, you should not take more than a minute to solve these kind of questions, right? But again, if you cannot solve it, I'm telling you the concept of these questions as well. So concept is very clear, right? For these metal rods, metal rod 1 and metal rod 2, both the rods, this is the rod 1, this is the rod 2, right? Think about it. What is really happening? They have the same length. So the length is not different. The length is same. Okay. Both of them have same length, right? And they have the same temperature difference between their ends. So actual temperatures at the end might be different, right? This can be 100, this can be 80. So the temperature difference is 20. For the second rod, this might be 0, this might be 20. Temperatures individually are different, but the temperature difference here is also 20, right? Okay, so their thermal conductivities are K1 and K2, right? So the temperature difference for this one is delta T, and for this one is also delta T, because temperature difference is same. Thermal conductivity is K1 here and K2 here, right? If the rate of heat conduction in first is 4 times, so basically rate of heat conduction through the first one is K1A delta T upon K1 sorry. Rate of heat conduction through the first one is going to be K1A delta T upon the length, right? They have the same length. Let's say the length is L. So K1A delta T upon L1 is same as K2A delta T upon L2, right? So area is cancelled out. Temperature difference is same across them. So K1 upon L1 is same as K2 upon L2, right? Yes or no? Yeah, but it is saying that the rate of heat transfer through the first one is 4 times the rate of heat transfer to the second one. So this 4 must be there, right? Yeah. So it is the rate of heat transfer to the first is 4 times than that of second, right? So 4 must be multiplied over here and rest of that is correct. Okay. Cross-sectional areas are not same, I guess, right? Cross-sectional areas are not same. It is A1 and it is A2. Okay. So now you can say that it is A1 and here it is A2, right? Because cross-sectional areas are not same. That is why you have A2 in the option. So no need to worry about that. Length are same, sorry. So length are same, right? So K1 A1 is 4 times K2 A2, right? So it's a direct 2-line questions, right? K1 A1 is 4 times K2 A2, which is the option A, and it is the correct answer, right? So you see that again, I'm telling you, in the NEET exam, these are single concept questions, right? Similarly, the question itself looks big, but it's a single concept question. And in the previous question, you have only 2 concepts, Wien displacement law and Stephen-Boltzmann law. That's it. So that is the limit of the questions, you can say. In the previous question, did I give you the quiz? Right? Yes, there was. Let's say that. Okay, no problem. So let's move on and talk about the next one. Look at this question. A cup of coffee cools from 90 to 80 in T minutes. When the room temperature is 20 degrees centigrade, okay, the room temperature is 20 degrees centigrade. Right now, what is happening? The heat is being lost to the ambient environment, right? The heat is being lost to the ambient environment. And my dear kids, in this particular situation, which law will help us? We can say Newton's law of cooling will work over here, right? The Newton's law of cooling will work over here, okay? A cup of coffee is cooling from 90 degree to 80 degree in T minutes when the room temperature is 20 degrees centigrade, right? So the time taken by similar cup of coffee to cool from 80 degree to 60 degree at a room temperature same at 20 degrees centigrade is going to be. So the question is very simple. From 90 to 80, the temperature taken is the temperature taken is T minutes. Then again from 80 to 60 for 20 degrees centigrade drop even further, right? At the same atmospheric temperature, how much new time will be taken out compared to the previous one, right? Is it 5 by 13 times of previous time? Is it 13 by 10 times of previous time? Is it 13 by 5 times of previous time? Or is it 10 by 13 times of previous time, right? So this is what you have to answer, right? This is what you have to answer, my dear kids, right? So think about it and try to solve it, okay? So think about it and try to solve it. So here, as I said, when a system is losing, here the cup of coffee is losing the heat to the atmosphere or ambient, right? Or surroundings. Ambience means surroundings, right? So when that happens, we can apply the Newton's law of cooling. So at what rate this thing will cool down? It clearly depends on what is the effective temperature of the environment, right? Okay. So clearly we can say that from Newton's law of cooling, so we have solved a question on almost each concept, right? From Newton's law of cooling, we can say that the rate of cooling of this cup dt upon dt, okay? The rate of cooling of this cup dt upon dt, right? How quickly the temperature is changing. The rate of cooling of this cup is a constant K times the initial temperature of cup and final temperature of cup by 2, and you have to use atmospheric temperature over here, right? Minus atmospheric ambient temperature over here, right? So this is how quickly the object is going to cool down. I hope that is very, very clear, right? So what is the rate of cooling? So rate of cooling is going to be here, if you talk about this thing. So dt is temperature difference, final temperature minus initial temperature, and dt, this is time. This is what? Time, okay? So this is the rate of cooling, how quickly that temperature is dropping for that particular coffee, right? So there are two cases as it is given in the question. In the first case, it is 90 and this is 80. It is cooling from 90 to 80. So for the case 1, it is 90, it is 80, and time is t, right? So 90 minus 80 upon t, which is 10 upon t, equals to k times ti plus tf, which is 90 plus 80 by 2. So 90 plus 80 by 2 minus TO, T0, or we can call it TO. It is surrounding temperature, which is 20 degrees. So you put 20 over here. So from the first expression, you will get something about the time, right? T in terms of K, okay? And in the second part, what you can do is, in the second part, again, use the same expression. In the second part, when the object is cooling, so final temperature is 60, initial is 80. So 80 and 60, difference of that is 20 degrees upon time. We don't know. Let's say the new time is t dash, right? It is k 80 plus 60 by 2 minus surrounding is still 20, so 20, right? In both the cases, you have a relation for t and t1, and you can solve it. That's it. So yeah, same relation is written over here. This is Newton's law of cooling, and for the first relation, you have this thing, this whole thing. So this 90 minus 80 upon t is equals to k, right? So k will be 10 upon 65 into t. This is the first condition. This is the first condition you have, right? So in the second condition, again apply the same formula. You have to cool from 80 to 60. So 80 minus 60 upon, let's say the new time is t dash. So 10 upon 65 t, and solve it. So you have 10 upon 65 t. So in place of k, so k, the value of k you have got from the previous solution. So just put it from k over here, and you get a relation between t dash and t. 13 by 5 times this thing, okay? 13 by 5 times this thing, t, right? So the new time is going to be 13 by 5 times of previous thing, okay? I hope there is no confusion in this part as well. So slightly lengthy problem, I would say, but nothing very difficult in this one again. Now look at this thing. So again, now we are jumping into another chapter, right, of thermodynamics. So here what is happening? We have two gases A and B. We have two gases A and B, right? So they are at the same pressure. They are at the same pressure, right? And they are the pressure in separate cylinders with movable pistons of radius RA and RB. Okay, so gas A is in one cylinder and gas B is in another cylinder. One cylinder has a radius RA, the second cylinder has a radius RB. On supplying an equal amount of heat to both the systems, we are supplying equal amount of heat to both the systems. So this is the first cylinder, just for the imagination purposes, right? So this is fitted with a piston. The second cylinder is also fitted with the piston. This one has a radius RA. This one has a radius RB, right? Here we have a gas A and another gas B, right? Both of them are different gases and they are filled at the same pressure. So pressure here is P and pressure here is also P, okay? Right. So on supplying an equal amount of heat, so what is happening? Heat is being supplied, okay? Heat is supplied, okay, to both the systems reversibly under constant pressure. So heat is supplied reversibly. So we are supplying at a very, very slow rate. So at a reversibly under constant pressure. So the pressure is constant. Pressure is constant. The easy way to visualize the constant pressure is, you can think of some weight is placed on this one. An exact same weight is placed over here as well, because on both pistons we have same weight. So the pressure is same on both the pistons, right? Or that would be the case if the area was same, but right now you can get that force per unit area is same. Force per unit area is same. The weight might be different because the cross sectional area is different, but you will get an idea. Some weight is placed over here and some weight is placed over here, such that the downward pressure that they are exerting is exactly the same, right? So the pressure remains the same, okay, under constant pressure. So heat is added at a constant pressure. Heat is added at a constant pressure. This is how you will take a note of this thing, okay? In thermodynamics, the process is defined by this thing, right? What is one thermodynamic variable that is kept constant, right? So that will decide the type of process. So here, whatever process is happening, we are heating up the system, but at the constant pressure. So you see that this line is very important. Heat is supplied at a constant pressure. That line should trigger you at the constant pressure, right? Heat is supplied at a constant pressure. Okay. Heat is supplied at a constant pressure. This is something that is very, very relevant for you, right? So now the pistons of gas A and B are displaced by 16 centimeter and 9 centimeter. The piston of A and B are displaced by 16 centimeter and 9 centimeter, okay, respectively. So if you are heating it up, right, so what is happening? So this is displaced in this direction by 16 centimeter and 9 centimeter respectively. If the change in their internal energy is same, the change in internal energy is same. So over here the change of internal energy is delta U. Over here the change of internal energy is also delta U, okay. Then the ratio of RA upon RB is going to be. So basically, in short, what is the question? On both the cylinders, on both the gases, heat is supplied at a constant pressure, right? Heat is supplied at a constant pressure. Both of them have the same initial pressure, right? And due to heating, both of them have same change of internal energies, right? And the expansion, one has expansion of 16 and another has expansion of 9. So this one is expanding by 16 centimeter and this is expanding by 9 centimeter. We have to know the ratio of their radii RA and RB, right? We have to know the ratio of their radii RA and RB, right? Okay. Question is clear to you, everybody? Very nice. Okay. Very nice. So just think about it, how to solve it. So this is the question that was asked in the year 2025. So what are the concepts you can apply? So again, I will also start the timer. So if you know how to solve it, so you can start solving it right away. In the previous question, there was a timer. So it was 13 by 5t, 13 by 5t, which is option C. Okay. And Ananya was also correct in the previous question. Good. Very good, Ananya. So here we have it. Let's go for this question. So the concept over here is, so in this system, what is happening? The heat added is doing two things, right? Whenever you are heating the system, added heat can do two things, right? So this is the first law of thermodynamics. What is that? First law of thermodynamics, right? When the heat is added to the system, this is the system fitted with a piston and some constant pressure is there on it. So constant pressure is exerted on the gas. Some gas is filled inside, right? Now, when you are heating it up, right? So let's say the heat that you are providing is Q. The heat you are providing is Q, or you can call it delta Q, right? So delta Q is invested in two parts. A part of the given heat is invested to increase the kinetic energy and potential energy of these particles, or you can call it internal energy of these particles. So now particles were vibrating slowly, but when you heated it up, now they are oscillating violently like this, right? Now they are oscillating violently. So a part of the heat given is invested to increase the internal energy, and another part of the heat that you have provided is invested to expand it, right? To expand it. First part is invested to increase the internal energy and second part is invested to expand it. So that is basically the work, right? So delta Q is equals to delta U plus delta W. This is the main idea, right? What is delta W? It is P delta V at the constant pressure, right? Okay. So at the pressure P, if the volume changes delta V, then the work done will be P delta V, right? V is the volume. I hope that is very, very clear. Okay. So once you know this basic concept, this is the first law of thermodynamics, you can talk about this part, right? So here we have these two cases and we know that the change of internal energy is same for both of them, right? The change of internal energy is same for both of them, and also they are giving us an equal amount of heat is supplied to both the systems, right? So you see that the delta Q is also supplied, which is same for both the systems, right? Delta Q is also supplied, which is same for both the systems, right? Now if you apply the first law, all you have to do is you have to apply the first law for this one and first law for this one, and the ratio of radii can be figured out very, very easily. Okay, right? So just apply the first law, right? So first law of thermodynamics, for the first system, delta Q equals to delta U plus delta W. everything for the gas A, right? So delta Q is equal to delta U plus delta W is P delta V. So P delta V. So for the first chamber, for the first piston cylinder arrangement, right? For the first piston cylinder arrangement, let us say the cross sectional area is A1, right? Cross sectional area is A1 or a cross sectional area of A, right? Whatever, right? And we can say the increase is happening. You see that the piston was initially here and now it is expanded by 16 centimeter. So what is the net volume which is changing? Net change in volume, delta V. Delta V is going to be change in volume is going to be area into height, right? So area is A, height is 16, okay, centimeter. So this is going to be the change in volume over here. So this is what we have done over here, right? P delta V, 16 into cross sectional area, right? Similarly, for the other gas, we can apply the same stuff, delta Q equals to delta U plus delta W for the second gas. And now the question is saying that both of the systems are getting the same amount of heat. So delta Q for A same as delta Q for B, right? Both the systems are getting the same heat, right? And now what you can do is delta Q for the gas A is written this one, write it down over here. Delta Q for the second system B is written over here, write it down over here. In the question, the change of internal energy is also same. So that part and that part is cancelled out. So you see that the pressure variation PA into 16 into A and PB into 9 into AB. So that is also same. And it is also given in the question that the pressure in A and pressure in B is same, right? Both the things are happening at the constant pressure and pressure in both of them is same, right? So again, pressure and pressure will also cancel out. So 16 into area of the first one is same as 9 into area of the second one, right? So area of first one is pi into r square of the first one. Area of the second one is pi into r square of the second one. And once you equate them, Ra upon Rb comes out to be 3:4, right? So I hope the idea is very, very clear. The ratio is very clear, which is, Ananya is saying that correctly, that option is going to be 3:4. Right. So I hope another concept is very, very clear. And now we can move on and talk about one more question. Right. This question was there in 2024. Right. Again, a very recent question from the thermodynamics. So thermodynamics is a thermodynamic system. So you see that whenever you look at the question and it has a graph, right? So I have seen that in the recent year, NEET preferably ask the questions on graph because it can test multiple concepts in one go, right? So a thermodynamic system is taken through the cycle A, B, C, D, A, right? So this is how the thermodynamic system is happening. Thermodynamic cycle is happening A, B, C, D, A. The work done by the gas along the path BC. What will be the work done by the gas along this path? Along this path, BC. So we can say that work done in a process is P delta V. Look at this path. Here the volume is not changing, right? Here we have pressure and here we have volume. So in the process BC, the volume does not change, right? The volume is same at B and C. So if the change in volume is 0, what will be the value of work done? Right? 0, right? What will the value of work done? 0, right? So the change in this process B to C, the change in volume is 0. So the work done will also be 0. So option A has to be the correct option. Very simple question. Look at that, this question, a sample of 0.1 gram of water, right? A sample of 0.1 gram of water, okay, at 100 degrees centigrade and normal pressure requires 54 calorie of heat energy to convert to steam at 100 degrees Celsius. If the volume of the steam produced is 167.1 cc, the change in internal energy of the sample is, what will be the change in internal energy of the sample? What will be the change in internal energy of the sample, right? This is what you have to figure out, right? What is given in the question? A sample of 0.1 gram of water, right? So this is the sample of 0.1 gram of water. Initially it is given to you, right? How much water you have? You have 0.1 gram of water, right? It is at what temperature? 100 degrees centigrade. And at what pressure? 1.01 10 to the power 5 atmospheric pressure, right? It requires 54 calorie of heat energy. So you can convert that into joules, right? Okay. You can convert that into joules, right? and it requires that much energy to be converted into steam, right? So you provide that much energy, it is converting into steam at 100 degrees Celsius, right? So all the energy is given in as a latent heat, right? Because water was already at 100. Okay, think about it. If the water was at 80 degrees Celsius, first of all, you have to provide heat so that its temperature can reach to 100. Once the temperature of the water, it is W, 100 degree centigrade. From 80 degree centigrade water, we have to first convert it to 100 degree centigrade water. And here the heat provided is Ms delta T. Now, at 100 degree centigrade water, whatever heat you have provided is the latent heat. And here you have 100 degree centigrade is steam. Right. That means you have provided latent heat. What you have provided? Latent heat. Okay. If the volume of the steam is produced is 167.1 cc, the change in internal energy of the sample is. So the change of internal energy of the sample you have to figure out. So my dear kids, the change of internal energy of the sample you have to figure out. Okay. So this is what you have to think about. Okay. So the heat you have provided is delta Q is going to be given directly. It is 54 calorie. It is latent heat that you have provided. 54 calorie, that means 54 into 4.18 joules. That much heat you have provided to the system in this conversion from 100 degree centigrade water to 100 degree centigrade steam. This much heat you have provided, right? And now you know that whatever heat you give to the system is invested in two parts. A part of that heat is converted to increase the internal energy of the system, and a part of the heat is invested to do some work. Okay. So we can say that whatever heat we have given in this process, delta Q, that is invested in delta U plus delta W from the first law of thermodynamics, right? So delta Q is given 54 into 4.18, right? Delta U is the change of internal energy that you have to figure out, right? And delta W, right? Delta W is the work done, right? So work done in this expansion, some work is also being done. The water is expanding, right? And the new volume is 167.11 cc, right? So here the delta W will be P delta V. Okay. So the pressure over here initially was this, right? Because we are heating up the whole thing at this pressure, right? So the pressure is given in the question. It is given in the question. How much is that pressure? 1.013 10 to the power 5. Okay. And delta V, what will be the change in volume? So my dear kids, the final volume is 167.1 cc, right? 167.1 cc, right? And initially we have only 0.1 gram of water. So compared to this steam volume, we can assume that this volume is negligible, right? We can assume that this is negligible, 0. So because we have to convert cc means centimeter cube, right? So we have to convert into meter cube. So we will multiply 167.1 into 10 to the power minus 6 minus 0. Okay. So once you do that, you can calculate delta U. You can calculate delta U, right? Delta U is going to be 208.7. Delta U is going to be 208.7, right? Just solve it, and this is what it comes out. Right, I solved it before the class and I have solved it multiple times. So I do remember this question. So delta U, once you solve it, will come out to be option B, right? Yeah. Right. So again, you see, the question itself is just 3 lines long. The solution itself is just 3 lines long. The thinking behind this question is something that you need with practice, right? Okay, now look at this question. A system is taken from the state A to B to C to D, right? Okay, no. This is not a cycle. It is not coming back. You see that these arrows are in this way and these arrows are in this way. So this is not one cycle. Okay. So what is happening? A system is taken from state A to a state C. From A to C following two paths, ADC and ABC. Okay. So we are moving from A to C in following two paths, ABC and ADC. Okay. Right, now you can get the arrows. The internal energy at A is 10 joules. Internal energy over here is 10 joules. Okay. Along the path ADC, the amount of heat absorbed dQ is 50 joules along the path ADC. So along this path ADC, the heat absorbed is 50 joules, right? You're calling it dq1. All right. And the work obtained is 20 joules, and the work obtained in this process is dw1. You can call it 20 joules, right? Okay. Internal energy at A is also given. You can write down in over here. So 10 joule is the internal energy at A. Okay. Whereas along the path ABC, the heat absorbed dq is 36 joules. So along the path ABC, the heat absorbed is 36 joules. Okay. The amount of work along the path ABC is going to be. So what will be the amount of work along this path? My dear kids, over here, you need to understand what is the difference between a thermodynamic property and a path function. My dear kids, the work done and the heat that you have to provide, right? These are not the point variable. For example, you cannot tell that at point A, this much heat we have in the system. At point C, this much heat we have in the system. At point A, this much work we have in the system. We cannot define the heat and work at a given point, right? But if you think about it, we can define what is the pressure over here, what is the volume over here. So pressure, volume, internal energy. Internal energy is a function of temperature. So if you know the temperature, you also know the internal energy. So pressure, volume, temperature, and hence the internal energy, right? These are the point variables. You can define these things at a given point. You can tell what is the pressure at A. You can tell what is the internal energy at A and what is volume at A. Similarly, you can tell what is pressure at C, what is volume at C, what is internal energy at C, right? So my dear kids, these are point variables, and it really doesn't matter what path you are following. For example, you follow any random path and come back at C. The pressure at C is given, right? The pressure at C is only this much. Yes or no? Right. So the pressure at C is independent of the path that you have taken. Once you are at C, the pressure is already defined. Yes or no? So for the point variable, the values of point variable is not dependent on the path you have chosen. Is that clear? The values of what you can say, the values of point variables like pressure, volume, temperature, and internal energy, they are point functions. They are not dependent on the path chosen. I hope the idea is very, very clear, right? So the internal energy, if you follow this path, you will get certain internal energy right now. Change of internal energy. Right now, the internal energy is 10 joule. Following the path number 1, you will get certain internal energy on this point, right? Even if you follow the other path, the internal energy at C, you are going to get the same because it is a point function, right? It is not dependent on the path. So following the logic, if you apply the basic concept, right, of first law of thermodynamics, you can say that dq1 is dw1 plus du1. So dq1 is 50. The work done in this one is 20. The change of internal energy in the first process is 50 minus 20. So delta U1 is how much? 50 minus 20, which is 30. All right. 30 joule. So from A to C, how much change of energy you are getting? 30 joule. That is the change of internal energy. From A to C, what is the change of internal energy? 30 joules, right? At A, the energy is 10 joules. And the change is happening 30 joule. So final internal energy minus initial internal energy is 10 joule, right? So final minus initial is 30 joule, right? So final minus initial. Initial is 10. That is 30. So clearly you can say that the internal energy at the final point will be adding up, right? The internal energy at final point will be adding up, right? So once you know the internal energy over here is 40, right? So that really doesn't matter you are following this path or the other path, right? I hope the idea is very, very clear. Once you know the internal energy, so right now in this process, you know dq is going to be 36, right? And the change of internal energy, right? 10 is here and 40 is here. So in this process also, the change of internal energy is going to be same because the initial and final points are same, right? So du in the second part is also going to be the 30 joule, right? So dw will be dq2 minus du2, right? From the second law, from the first law of thermodynamics again, dq minus du is going to be dw, right? So 36 minus 30, which is option D, right, is going to be the correct option. Okay. Option D is going to be the correct option. I hope it is very, very clear. Okay. So let's move on and talk about the next one. Next question is saying that the internal energy change in a system that has absorbed 2 kilocalorie of heat and has done 500 joule of work is, what will be the internal energy change of the system, right? What will be the change of internal energy of that system in which it has absorbed 2 kilocalorie of heat. So you can say that 2 kilocalorie of heat is absorbed and the work done is 500 joules. The work done is 500 joules. Right? Right. So just think about it. How much change of internal energy is going to happen? Right? Very simple concept, and you can think about it. Right? You can solve it. Okay. Just use your mind, and I believe these kind of simple problems you should be able to solve directly. Okay. Just one line solution is there. Based on the first law of thermodynamics, you can solve it directly. Right? So I have solved 2-3 questions on the similar concept. Think about it. Internal energy change is given 2 kilocalorie. Right? Okay, 2 kilocalorie. So we don't need in calories, we need in joules. So multiply with a certain thing. What is that certain thing? And then the work done is also 500 joule, right? The internal energy change system that has absorbed that much heat is this. So amount of heat absorbed is written and amount of internal energy change is written. Work we have to calculate, right? Okay. Very simple, right? Delta Q equals to delta U plus delta W, right? So delta Q is how much? Delta Q is 2 kilocalories. So that many 2000 calories and multiply by 4.18 or 4.2 simply to get it into joules. And delta U you have 500 and delta W you have to calculate. This is the only variable. Very easily you can get it. Okay. All right. So that's it. So let's say option 7900. Option C should be the correct option, right? Option C should be the correct option. Okay. So let's continue and talk about the next one, right? Over here, 1 mole of an ideal diatomic gas is undergoing a transition, right? 1 mole of an ideal diatomic gas is undergoing a transition from A to B, right? So this is how we are going from A to B, okay? Along a path AB, as shown in the figure, the change in the internal energy of the gas during the transition is. So what will be the change of internal energy in this process? Right, the change of internal energy during this process is going to be, right? Okay. Okay, that's what you have to think about, okay? So it was asked, it's a slightly good question, you can say. Slightly good question, right? Not very difficult. So you can say that slightly good question, okay? You have been given that this is a diatomic gas, right? And this diatomic gas is undergoing this pressure volume curve is given, PV curve is given, right? Okay. So from here, those who cannot solve it can look at the conceptual part of the solution. So the concept is this, right? In these kind of questions, we can go for the direct values of internal energies and all, right? Because we know that the internal energy of a system is NCV dt, right? Once you know a single process, right? Single thermodynamic process is given. So some temperature will be here, some temperature will be here at the end of the process. So that will give you a temperature difference. So during any thermodynamic process, if you know the temperature difference is delta T, the internal energy in that process is involved. The internal energy change in that process is going to be NCV delta T, right? The internal energy change in that process is going to be NCV delta T. So internal energy change, I should call it, is NCV delta T, right? My dear kids, it is also possible that you don't have a temperature versus other graphs, right? You don't know directly, like the temperature graph is not given, right? Here you don't know what is the difference of temperature you will have, right? But the pressure and volume values are given. So by knowing the pressure and volume at a certain place, you can know the temperature at that place, right? So that is not a worrisome point. You can talk about that. PV equals to nRT, right? PV equals to nRT. By knowing the pressure and volume, you can get an idea about the temperature at that place, right? So following these two logics, you can solve this particular question, right, and get to the solution part. Okay. For diatomic gas, what is the value of N, right? What is the value of, CV? What is the value of CV for diatomic gas? We can say that if the gas is diatomic, it is 5 by 2 into R. Yes or no? For diatomic gas, right? And delta U equals to NCV dt. So dt, delta T is initial temperature minus final temperature. The temperature here and temperature there, right? So final temperature minus initial temperature. So this is the arrow, right? So this is the final temperature, this is the initial temperature. So what will be the temperature over here? We don't know. We know the pressure and volume over here, right? So final temperature is at B. So since we don't know the temperature at B directly, you can write it first, TB minus TA, right? So since we don't know the temperature at certain place, so temperature at a certain place is going to be PV upon NR. Yes or no? Temperature at a certain place is going to be PV upon NR. So temperature at B is going to be pressure at B, volume at B upon N and R minus pressure at A, volume at A upon N and R, right? Okay. So N into 5 by 2 into R, right? That is equals to change of internal energy. Now you see that if R we have taken out, so that is going to cancel out, right? Okay. And if N is taken out, the N will also cancel out, right? So N and R will cancel out from here. I believe this is very, very easy for everybody to understand. So we have 5 by 2 PBVB minus PAVA. Now if you look at the question, PB and VB, pressure at B is 2 kilopascal, pressure at A is 5 kilopascal. So PB and PA and PB are given. And similarly, VA is 4 meter cube, VB is 6 meter cube. So VA and VB are also given, right? So both the values you already know, right? You can put the values of PB, VB, PA, VA, you will get the answer, right? You will get the values, you will put the values, you will get the answer, right? So pressure at B is, when you going to put the value, pressure is given in kilopascal. Pascal is Newton per meter square. Kilopascal. So you can when the answer is Newton per meter square, it is already SI. Pascal is already SI unit. Kilopascal is 10 to the power 3, you have to multiply. So PB is 2 kilopascal, which is 2 in 10 to the power 3 pascals. Volume at B is how much? Volume at B is 6 meter cube, so you don't need to convert it. Pressure at A is 5 kilopascal, so it is 5 into 10 to the power 3. And volume at A is going to be 4. Okay, so just multiply it and you will have your answer of delta U. Okay, I hope the idea is very, very clear. Now look at this one. If Cp and Cv denote the specific heat per unit mass of the ideal gas of molecular weight m, then where R is molar gas constant? So this simple relation you have to tell that, right? Now you can tell this particular thing directly, okay? Right. If Cp and Cv denote the specific heat per unit mass, Cp and Cv are specific heat per unit mass of an ideal gas of molecular weight m, right? Molecular weight m. Then what will be the relationship between gas constants, right? What will be the relationship between the gas constants? So clearly, because you know the molecular mass, Cp and Cv are molecular specific heats of an ideal gas at constant volume. So basically what is given? Cp is m times small cp. So you see that when we write down the difference now, Cp minus Cv. So there we are not considering that for the entire mass, right? So you see that for the mass m, the Cp, capital Cp is m times small cp, specific heat capacity, right? So here similarly for the entire mass m, Cv is going to be m times Cv. Per unit mass it is small cv. For the entire mass m, it is m times Cv. Cp minus Cv is R, we know, but this is small cp. Cp minus Cv is R. So now in terms of small c values, because in the answer there are small values, right? So if you just put the values over here, right, you will get it. Cp minus Cv is going to be R upon m, right? M upon m will come from that side, right? So Cp minus Cv will be R upon m. Okay, so option C will come out to be the correct answer. Now look at this one. The equilibrium state of the thermodynamic system is described by. The equilibrium state of a thermodynamic system is described by. My dear kids, pressure, total heat, temperature, volume, work done. What will decide the equilibrium state? State, right? The state is decided by state variables. For example, this is the thermodynamic process between pressure and volume are given, right? So here, if you want to define this state, you will define the pressure over here, you will define the volume over here, you will define the temperature over here. You can also define the internal energy over here, right? But you cannot define the work done at this point. You cannot define the heat added at this point, right? Because that can only be described for a process, for a path, okay? Those are path functions, okay? So a state can be defined by pressure, volume, temperature, internal energy, and a process state needs the path variable, not the state, right? Okay. So pressure is something that you need to define equilibrium state. Total heat cannot be used to define the equilibrium state. Temperature can be defined. Volume can be defined at a state. Work done cannot be defined at a state, right? So this is also not the answer. So we can say except B and E, rest are correct. So A, C and D are correct. So option D is correct. Okay. So this is again was in 2024. Light concept. Swapnil. Swapnil is asking, when is the faculty reveal of Arjuna NEET? Soon. Right. Soon it's going to happen. All right. A cylinder contains hydrogen gas at a pressure of 249 kilopascal and temperature of 27 degrees centigrade. Its density is going to be. So what will be the density of this particular thing, right? What will be the density of this particular thing, right? So very simple question again. Okay. So think about it. We have a cylinder that contains hydrogen gas at a certain pressure of 249 kilopascal. We have a cylinder that contains hydrogen gas at a pressure of 249 kilopascal. So pressure is given 249 kilopascal. Okay. And temperature is given 27 degrees centigrade. Temperature is given 27 degrees centigrade. All right. Its density is going to be. So what will be the density? Okay. At a certain pressure and temperature, density must be defined now. So what will be the density of this thing? Think about it. Very good. Okay. Chalo, let's have a look at this particular value as well. Okay. Now, my dear kids, we know that PV equals to nRT, right? Here we are interested in pressure, temperature, and density. Pressure, temperature, and density. Density can be written by D, or density can also be written by rho, whatever you like, right? Pressure, temperature, and density. These are the values you have to talk about, right? So now, if I talk about these things, so this relation is something that we know from the very beginning for any ideal gas, right? You know that. Now, the N is described as the mass upon molecular mass, right? M upon M, right? You know that, right? Okay, ulta likh diya. So N is described as upon per unit mass, right? Like this, okay? So now, if I think about it, density, if I want to convert this expression in terms of density, so density is mass per unit volume. Mass per unit volume, okay? So how can I get that, right? How can I get that? Very easily. I can simply put this relation in terms of density. How can I get that? I can get this relation in terms of density, right? So Right. So now if you think about it, pressure into mass will be rho r and t. Think about it. How did I get that? Right. Pressure into mass is going to be rho r t. Okay. And from here, the density can be written as Pm upon RT. Right. So just think about it. Okay. Rho is density is going to be Pm upon RT. Pm upon RT. On RT. Right. So here mass of the gas is given. Okay. Everything is given and we can just solve it directly, right? Pressure is given 249 kilopascal, right? Pressure is given 249 kilopascal. Okay. And at a pressure of this thing, and temperature is given 27 degrees centigrade. Everything we have to put in Kelvin because the value of R is also given in Kelvins. So the temperature is 27 plus 273, which is 300 Kelvin, right? And it is a hydrogen gas, right? A cylinder contains a hydrogen gas. So what will be the mass? We can say 2 into 10 to the power minus 3. Okay. M is going to be 2 into 10 to the power minus 3. Pressure is given 249 kilopascal. So 10 to the power 3 से multiply कर लो. So value of R is given already 8.3 and value of temperature is given 27 plus 273, right? So everything is already given to you. You can just put the values and you will get the values of rho. Okay. All right. Okay. Now let's move on and talk about the next one. For the given cycle, the work done during the isobaric processes. So which one of these processes is isobaric? In this cycle, there are 3 processes. Which one of them is isobaric? First of all, think about it. Which one of them is isobaric? Okay, isobaric means the process in which anything can change but at the same pressure, right? Pressure will not change in the isobaric process, right? The pressure will not change in the isobaric process. Pressure is constant. Okay. In the isobaric process, what is constant? Pressure is constant. In which process pressure is constant? We can say, look over here. This is the pressure axis. This is the pressure where, this is the process where the pressure is constant. From A to B, the process from A to B is the isobaric process, right? The process from A to B is the isobaric process. Okay. The process from A to B is the isobaric process. So think about it. How much work is done during the isobaric process? So work done in the isobaric process will be P delta V. Because it is isobaric, the pressure over here is this 3 into 10 to the power 2. What is volume change? Here you see that the volume change is written in meter cube. Final volume is 3 meter cube. Initial is 1. So 3 minus 1. Delta V is also there, right? Delta V is also there. So both the values you know already, right? Okay. Pressure is 3 into 10 to the power 2. And the volume change is 3 minus 1. That's it. Work done you can calculate. It is 6 into 10 to the power 2. 6 into 10 to the power 2, which is 600 joule. Option D is correct option, right? Okay. Now have a look at the next question. Now have a look at another question. An ideal gas undergoes 4 different processes. 1, here the volume is constant. 4, the pressure is constant. And in between, we have 2 graphs of different slopes, right? One that has a steeper slope and one that has a smoother, lesser slope, right? So the process 2nd is happening much faster. Process 3 is happening at a slower rate. The slope defines how quickly the change is happening, right? Okay, these processes are adiabatic, isothermal, isobaric, isochoric. So clearly, if I have to tell that this is isochoric process, volume is constant. This is isobaric process, pressure is constant. And the process where the rate of change is higher is adiabatic. So second one is adiabatic. And here the process where the changes are slow is isothermal process, right? So the curve which represents the adiabatic process among these is, so in all 4 of them, which one represents the adiabatic? The second one represents the adiabatic process. So option B is the correct option, right? Okay, option B is the correct option. Okay. All right. So let's move on and talk about the next one. Look at this question. Two cylinders A and B of equal capacity are connected to each other via a stop clock. A contains an ideal gas at a standard temperature and pressure. B is completely evacuated, right? Two cylinders A and B of equal capacity are connected to each other via a stop cock. Matlab, we have one cylinder, right? We have another cylinder, right? They are equal capacity cylinders. They are connected by a stopcock like this, right? So we can allow the flow of gases or fluid, whatever it is. We can allow the flow of things in fluids inside each other by opening or closing this stopcock, right? A contains an ideal gas at a standard temperature and pressure, right? B is completely evacuated. So in B there is here we have ideal. Here A contains ideal gas at a standard temperature and pressure, and here we have vacuum, right? The entire system is thermally insulated, so no heat is added to the system, removed from the system. The stopcock is suddenly opened. What will be the process? So clearly we can say that if a stopcock is suddenly opened, here we have standard temperature and pressure, so pressure is higher on this side, here we have vacuum, pressure is low on this side. The gases will automatically, like instantly the gases will expand, right? So the gases are expanding, and the change of pressure and volume is happening at a much faster rate, right? So we can say that here once you open it up, gases are going to expand all of a sudden, right? So you see that the change is happening at a much higher rate. So you can call that as an adiabatic process, right? So when the changes are happening at a much faster rate, you can call it an adiabatic process, right? And of course, in the adiabatic process, the system has to be thermally insulated. So no heat is added to the system, no heat is removed from the system. That part is also taken care of because it is written, it is thermally insulated. The system is thermally insulated, right? So that part is also there, right? Let's move on and talk about the next one. In which of the following processes heat is neither absorbed nor released by the system, right? So in these four processes, in which one heat is neither absorbed by the system nor released by the system? As I said, it is adiabatic, because in the adiabatic system, the system itself is thermally insulated from the surroundings, and since it is thermally insulated, it is this, right? It will neither take the heat from the system nor it will give the heat away from the system, right? Okay. Now the next question is the volume of an okay, a monoatomic gas varies with temperature, right? Volume is varying with temperature, so volume temperature graph is given, okay? The ratio of work done by the gas to the heat absorbed by it when it undergoes a change from state A to state B. So state A is somewhere here, state B is somewhere here. So what will be the ratio of heat absorbed by it when it goes change from the ratio of work done by the gas to the heat absorbed by it. Okay, so the process is happening from A to B. In this process, it is going to do some work and it is going to absorb some heat, right? Because the temperature is increasing, so it has absorbed some heat, and in this process, because the temperature is rising and volume is also rising, right? So some work will be done as well, right? So you see that again, listen again. System is expanding, some work is done, P delta V, and the temperature of the system is also rising, temperature is also rising, so some heat must be added, right? So the heat added from A to B is delta Q, the work done is delta W, right? The work done is delta W. So both the things are there. We have to find the ratio of delta Q and delta W, right? What will be the ratio of these two things? What will be the ratio of these two things, right? So this is what we have to figure out. Think about it. Right? Okay, so just think about it. You can have your time, you can think about for a minute or two. Okay, very good, Ananya. Okay, so you have a minute to think about, right, about this question. So, decent question, you will say. So in a given process, you can directly tell that what will be the heat absorbed, right? Heat absorbed is going to be NCP dt, right? Heat absorbed is going to be NCP dt. Right? For this process, right? For this process, heat given is Cp dt, right? Cp dt. And remember that it is Cp, not Cv. Delta Q is NCV dt, right? So that's a different thing. And delta U Q is there, and delta W we don't know, but we know that PdV is equals to nRT. PV equals to nRT, right? Okay. So PdV is also work done, dW. So dW is equals to nRT. We can use that, right? Or the change of temperature is dt. So we can say that nR dt, right? So these are the two equations which will be helpful in this particular question, right? So because we don't know anything about the process, right? And we only know that some temperature will be here and some temperature will be there. So how much heat will be added during this process? So NCP dt is the heat added during this process, right? And how much work is done? It is PV is equals to nR dt. nR dt is the amount of work done, right? In terms of temperature difference. Okay. So if you use that, you can easily calculate it. So what will be delta Q upon delta W? For monatomic gas, Cp is equals to 5 by 2R. It is 5 by 2R for monatomic gas. It is given the question. So N into Cp dt, N into Cp and dt, right? Tb minus Ta upon Nr dt. All right. So clearly the ratio will come out to be N and N, R and R, delta T and delta T will cancel out. The ratio will come out to be 5 by 2, right? And we have to answer actually the ratio of work done by the gas to the heat absorbed. Work done upon heat absorbed, we have to figure out ulta. Delta Q upon delta W upon delta Q we have to answer, right? We have to answer delta W upon delta Q, work done upon heat absorbed. So it will be just opposite of that, 2 by 5, right? So anyone who knows these two basic formulas can just take the ratio and get the answer 2 by 5, right? Anyone who knows the basic formulas, we can talk about that. One shots of this chapter are posted. Ritika, all right, you were watching those. Great to hear that. But since we are shifting towards exam kind of environment and these series were to be brought up, that is why I'm not getting enough time to record those one shots. But anyways, since you are following them religiously, so I'll try to find some time and post it. Okay. If anyone is studying seriously, then I must post it. Okay. So let's keep on moving and talk about the next part. 1 mole of an ideal monatomic gas undergoes a process described by the equation PV to the power 3 is constant. The heat capacity of the gas during the process is. So what will be the heat capacity of gas during the process, right? Again, a very easy question, right? Think about it. Use your own brain as well. Okay, wait a second. In the previous question, what was the answer? 2 by 5. So option A was correct. Okay. In the next question, 1 mole of an ideal monatomic gas undergoes a process described by the equation PV to the power 3 is constant. Very simple question, right? The heat capacity of the gas during the process is. So what will be the heat capacity of the gas during the process? Sure, Ritika, sure, right? What will be the heat capacity of the gas during the process? Think about it. If we have a process where PV to the power n is constant, so what kind of process is it? We can say that we have a process called PV to the power concept. We have a process PV to the power n is constant, right? Such a process is called as polytropic process. What do you call it? Polytropic process. We can call it polytropic process. What you can call it? Polytropic process, right? Okay. So for a polytropic process, we need to find the heat capacity. So heat capacity will be, for a polytropic process, the heat capacity for a polytropic process is Cv plus R upon 1 minus gamma, right? Sorry, 1 minus alpha, right? Okay. I hope that is very, very clear, right? So PV to the power 1 minus alpha, because I have written here is n. So R upon 1 minus n, I can write it, okay? So if we have a process, PV to the power n is constant, then that process is polytropic process, and for a polytropic process, the specific heat capacity is Cv plus R upon 1 minus n, whatever that power we have over here, right? Okay, so we have monoatomic gas. For a monoatomic gas, Cv is 3 by 2 R. Cp is 5 by 2, right? Cv is 3 by 2 R, right? Okay. And we have n. N is PV to the power n. In place of n, we have 3, right? R upon 1 minus 3. Okay. So that is the answer. So 3 by 2 R plus R by 2. So 4 R by 2, which is 2 R. So option C is the correct option. I hope that is very, very clear. All right. So let's keep on moving and talk about the next part. Now in this question, the figure shows that this should be 2R. Okay. In this question, the figure shows that there are two paths that may be taken by a gas to go from a state A to state C. Okay. So we can go from A to C following this path and following this path. So we have solved similar question like this. You see that it is asked in 2015, and the question that we had solved, the two path problem, it was asked much recently, right? If I have to show you this question I am talking about, where is that question? Not this one, where we have applied the first law of thermodynamics on two different processes. This one, right? A system is taken from two different paths, right? So here you see that similar kind of problems was asked again in the NEET exam. So you see that solving a good kind of questions will help us in more than one ways, right? So figure shows that there are two paths that may be taken by a gas to go from state A to state C. This path and this path, right? In the process AB, okay, in the process AB, 400 joule of heat is added to the system. Okay. So in the process AB, let us, in the process AB, 400 joule of heat is added to the system. Okay. And in the process BC, 100 joule of heat is added to the system. In the process BC, 100 joule of heat is added to the system. Okay. The heat absorbed by the system in the process AC will be, heat absorbed by the system in the process AC will be. So in this process, how much heat will be absorbed by the system in the process AC, right? Clearly, heat absorbed is a path function. So in this path, this much 400 plus this much 100 joule, 500 joule heat is required. But if you follow this path, same amount of heat will not be required, because heat required in a certain situation, heat required in a certain process depends on the path you have taken, right? Even if the end positions are same, end thermodynamic states are same, A and C, these process and this process will not require the same amount of heat. Both the processes will not require same amount of heat, right? Both processes will not require same amount of heat. We can calculate those things, right? We can calculate those things. So again, very simple type of question is this, but I would want if you can think about this question for 1 minute, right? It will help you in more than one ways to deal with this kind of question in the main exam, right? My dear kids, if I again one hunch you will have, right? You may have a feeling that we have to apply the first law of thermodynamics, right? So first law of thermodynamics talks about three things. What are those three things? It talks about work done, it talks about the change of internal energy, and it talks about the heat supplied, right? So we know the idea of heat supplied, right? The change of internal energy in this process and in this process will be same because the end positions are same, right? This is the question that we have already solved, right? Because internal energy is a state function, right? So if you follow the first path or if you follow this path, the change of internal energy is same. So if I have to write it out somewhere, the change of internal energy, we have to talk about three things again: heat, internal energy, and work done. So the first thing is internal energy. It is same for ABC, delta U for A, B, C, and delta U for A to C is same. The change of internal energy is same for both the processes, right? Okay. Once you know that particular part, we can go ahead and talk about the next part, right? The change of internal energy is same for these two processes. The change of internal energy is same for these two processes, right? This is the first hint you have. Now think about it. From A to B, from B to C is a isobaric process. We will be doing some work. Now we have to think about work, right? In discussion of internal energy we have done, right? Now think about the work done. Three things we have to think about to apply the first law of thermodynamics. Think about the work done. In this process, there is it is at a constant volume. A to B is a constant volume. So work done in this process, delta W will be 0, right? P delta V, right? So delta V in this process is 0, same volume during the process. So work done will not be there, work done will be 0, right? And in this process, work done will be, during BC will be P delta V by, right? So work done during the process BC is P delta V, right? So the pressure over here is 6 into 10 to the power 4 Pascal, right? And delta V is from here to there, right? So 4 into 10 to the power minus 3 minus 2 into 10 to the power minus 3, which is subtract them. 4 minus 2 is 2. So 2 into 10 to the power minus 3. So this is going to be the work done, right? So in the process AB, no work. In the process BC, the work done is this much. So we can say that total from ABC, work done in the process ABC is 0, or you can say work done from A to B plus work done from B to C, right? 0 plus this value, right? So basically we can calculate the work done in the process ABC. Now, my dear kids, we know that the work done in this process is something that we have already figured out. Heat required in this entire process, heat in this process plus heat in this process. Here in this one, 400 joule, in this one, 100 joules. So heat required in the process delta Q in the process ABC is 100 plus 400, which is 500, right? So we know delta W for the process ABC, this plus this, delta Q for the process ABC. So from here, we can calculate delta U for process ABC, right? Some value, right? Once you have calculated the change of internal energy between A and C in this process, we can say that the same change of internal energy will be there in this process as well from A to C. Once you know delta U, right? Now we can apply the first law for the process AC. And you will say that delta Q for AC is delta U for AC plus delta W for AC. So clearly delta Q will be delta U for AC, which is same for the previous case situation that you have just calculated, this one, right? Delta U for AC, this is going to be same because for both the processes, initial and final positions are same. So delta U will be same, right? Delta W for AC, how much work is done in this process, right? So how much work will be done in this process? That is something we can put over here, right? How much work is done in the process A to B, okay? That we can put over here, okay? A to C, sorry. That we can put over here and calculate it. Right? Think about it. Think about it. Right? Just use your brain. How will you calculate the work done in the process A to C? You know the pressure at A, you know the pressure at C, you know the volume at A, you know the volume at C, right? Think about it. So work done in the PV diagram, how will you calculate that? Use your brain. Pressure is given. Okay. Very easily we can calculate that now. So work done during the process AC. Work done during the process AC will be over here we have P and V, we know already. 2 into 10 to the power 4 is the pressure over here. Right. Multiply that by volume here is 2 10 to the power minus 3 minus 1 upon 2 P2 and V2. So pressure over C is pressure over this particular point is 600 to the power 4. Right. And the difference of volume over here, is 4 and 2, right? So the value over here you can put 4 into the power minus 3, right? 4 into the power minus 3 minus this particular thing. So it's going to be 4 minus 2, which is going to be 4 minus 2, which is going to be 2 power minus 3. All right. I hope the idea is very, very clear. 6 is this value. 6 is this entire value. We have to put this value, na? We have to put this value. So it is 6 minus 2, it is 4. I should be using 4 over here. So now it is correct, right? Now it is correct. Okay. So this is going to be the value of work done at this particular process. Okay. This is going to be the value of this particular process, right? Okay. So now you know everything, right? Delta U you have calculated from the previous process. Work done you have calculated over here by looking at the area, right? And now you can calculate delta U, right? Delta Q in the process AC very easily. Just add the values up, right? This is a numerical value and this is also a numerical value. Just add these values up, you can get the final answer, right? Just add the values up and you will get the final answer, right? Okay. So this is what they have done as well. So first of all, they have followed one process, right? And in the first process, they have calculated the value of change of internal energy, right? So this comes out to be minus 20. So change of internal energy is going to be same for both the processes, right? So whatever that change of internal energy you are getting, you can put it over here, right? Change of internal energy you are getting, you can put it over here, right? And from that you can calculate it in the second part, right? From that you can calculate it, right? So now the next part is this, okay? During an isothermal expansion, a confined ideal gas minus 150 joule of work is done against in surrounding. This implies that what is really happening is minus 150 joule of work is done against a surrounding. Minus that much work is done against the surrounding. So what is the correct thing to say? 150 joule of heat has been removed, right, from the gas. No, it is the work against the surrounding. That means heat is added to the gas, right? So that much heat is added to the gas. Option D should be the correct option. Which of the following process is reversible? So which of the following process is going to be a reversible process, right? So think about it. Reversible process, that means you can get back to the same state, right? If you provide the similar conditions. Transfer of heat by conduction, is it a reversible process? Transfer of heat by radiation, is it a reversible process? Isothermal compression. So isothermal compression is happening at a very steady state. So ideally this process is the reversible process, right? A Carnot engine has an efficiency of 50% when its source is at a temperature of 327. What is the temperature of the sink? What is the temperature of the sink? So clearly, efficiency of the Carnot engine is 1 minus T2 upon T1, right? Efficiency of the Carnot engine is 1 minus T2 upon T1. Just a second. Efficiency of the Carnot engine is 1 minus T2 upon T1. And by using this logic, right, so here we have it. The efficiency of Carnot engine is 50% when the source is the temperature of 327 degree, right? So efficiency is 50% when the source is at the temperature of 327 degrees Celsius. So here you have to use in Kelvin. Here you have to use in Kelvin, right? So from here, you can calculate the value of T2, the temperature of the sink. T2 you can easily calculate from here, right? No need to worry about that. Very simple part. So you just put it, efficiency is 50%, so 50 by 100, 0.5, right? So, and 1 minus T2 upon 273 plus 327, which is given, right? So which is 600. So T2 can be calculated, it is here, right? The next one is this, Carnot engine having an efficiency of 1/10 as heat engine. So Carnot engine has an efficiency of 1/10 of the heat engine, right? Okay, and it is used as a refrigerator. Okay, if the work done on the system is 10 joules, the amount of energy absorbed from the reservoir at the lower temperature is going to be. So the idea is very, very clear, right? The simple formula of efficiency is used, applicable over here. We know that there is a relationship between the coefficient of performance. For heat engine, we define a term called coefficient of performance, right? For heat engine, we define a term called coefficient of performance. So that coefficient of performance for a heat engine is beta. And the efficiency of Carnot engine is alpha. Efficiency of Carnot engine is this, right? Now, we can relate the efficiency of Carnot engine and the coefficient of performance of a heat engine with this relation. We can call it beta is equals to 1 minus eta upon eta, right? I hope that is very, very clear, right? Now, we can put all the values, it is given in the question directly. A Carnot engine is having an efficiency of 1/10 of the heat engine, right? So efficiency is already 1/10 of a heat engine, right? Okay. So we can put the required value. If the work done by the system is 10 joule, the amount of energy absorbed from the reservoir at the lower temperature is going to be, right? So amount of heat absorbed, we have to figure out. So clearly eta here is 1/10, right? 1/10, we can put the value over here. This value is, we can put 1 by 10 over here. So 1 minus 1 by 10 is 9 by 10, and here is 1 by 10, so it is 9, right? So coefficient of performance comes out to be 9. Now what is coefficient of performance? Coefficient of performance is the desired output upon the input, right? Or the work done, right? So desired output of refrigerator is heat ejected to the atmosphere or the lower temperature or sink, right? Upon the work done is W, right? This is the desired output upon the input, right? Q2 upon W, okay? So, right, so what is really happening? The amount of energy absorbed from the reservoir at the lower temperature. So we are interested in this part, Q2, right? The work done here is given 10 joule. So this is 9, this is 10. Q2 is going to be 9 into 10, right? Which is 90 joules. Q2 is going to be 9 into 10, which is going to be 90 joules. I hope that is very, very clear. Now, look at this one. The following graph represents the TV curve of an ideal gas at 3 pressures P1, P2 and P3 compared with those of Charles' law, right? Charles' law. So that means Charles' law is saying volume is proportional to temperature at a given pressure, okay? So we are trying to draw volume and temperature curve at 3 given pressures, okay? So we want to know that which pressure is going to be higher, right? So, you know that from the Charles' law, volume is proportional to temperature, or V upon T is going to be constant, right? So the slope of this curve is telling us how quickly the temperature is changing with respect to volume, and that is going to be a constant, right? So my dear kids, from this expression we can say for a given volume, right, we have to talk about this part. Okay, we have to talk about this part where the pressure is going to be higher, right? Right, at 3 pressure compared to those of Charles law, then what is going to be the correct relation? Okay, so clearly it states that at a given volume the pressure in the first graph is higher, right? And then in the second one and in the third one, at a given volume the pressure is in the first one is highest, right? So option D is the right answer, right? So we don't have to think much about it. Okay, a container of volume 200 centimeter cube contains 0.2 mole of hydrogen gas and 0.3 mole of argon gas. The pressure of the system at the temperature 200 Kelvin is going to be. So what will be the container of the volume is given. Container of the volume 200 centimeter cube, right? This is the volume of the container. It contains 0.2 mole of hydrogen gas and 0.3 mole of argon gas. It is given in the question, right? 0.2 mole of the hydrogen gas and 0.3 mole of the argon gas. And the pressure of the system at the temperature 200 Kelvin will be. So what will be the pressure of the system at temperature 200 Kelvin? We can say that the pressure due to the combination of those two things, the pressure will also add up, right? And if the first one has the mole mu1, the second one has the number of moles mu2, then the total pressure is mu RT, but there are two gases, so mu1 plus mu2 into RT, right? Mu1 plus mu2 into RT, right? And it is PV equals to mu RT. So PV equals to mu RT. We just need to answer PV equals to mu RT, right? And the pressure at the system we have to talk about. So we only need pressure, right? So pressure is going to be mu1 plus mu2 into RT upon V, okay? So mu1 is given in the question 0.2 mole, mu2 is given 0.3 mole, R is the gas constant given here, T is the temperature given here 200 Kelvin, V is the volume given here 200 centimeter cube converted into meter cube, but multiplying it with 10 to the power minus 6, right? So everything is given. We can get the value of pressure from here, right? So nothing to worry about, very simple solution you can have, right? Yeah, same thing we have done. Okay. Now the next thing is the volume of volume occupied by the molecules contained in 4.5 kg water at STP if the intermolecular forces are there, right? So what will be the volume occupied by this thing at STP if the intermolecular forces vanish away? There are no intermolecular forces. So what will be the volume occupied by the molecules contained in 4.5 kilogram of water at STP? Okay. Think about it. At STP, we have to talk about the volume. So first of all, tell me what is the temperature at STP? Right. What is the temperature at STP? We can say that in Kelvin we have to put, right? So in Kelvin you can say that it is 273 Kelvin. Okay. All right. So approximate value we can use 273.15. So 273 Kelvin, right? And we have to talk about the volume over here, right? And what is the pressure? Pressure is at atmospheric pressure. So 1.01 10 to the power 5 is atmospheric pressure, but we can say it is only 10 to the power 5 or 1 into 10 to the power 5 Pascal for simple calculation, not 1.01, right? Okay. And now you need to think about, we have to talk about the volume, right? Volume occupied. So PV equals to nRT is the formula that we know. Or in terms of number of moles, because we are talking about number of moles, right? So mu RT, and volume is something which is mu RT upon pressure. Okay. So we know these things here because we have to calculate volume at STP. So temperature at STP will be used and pressure at STP will be used, which are these values, right? R is a constant 8.31. We can use that, right? And mu is the number of moles that you can get. So 4.5 kilograms are there, right? 4.5 kilograms of water, 4.5 kilograms of water, Okay. So what will be the number of 4.5 kilograms of water, right? So what is the molecular weight of water? So how will you figure out the number of moles, by the way, in 4.5 kilograms of water? So to figure out the number of moles in that much water, you have to divide whatever mass of water you have, you have to divide whatever mass of water you have with the molecular weight of water, with the molecular weight of water. That will give you the number of moles, right? So mass of water is 4.5 kilograms that you have. Molecular weight of water is H2O. For hydrogen and hydrogen 1 for oxygen it is 16, so 16 and 2 18, and in kilogram you have to put, so it's 6 because here you have kilogram, so both the units should be same, 4.5 upon 18 into the power minus 3, right? All right, so because in the numerator you have in kilograms, so the denominator should also be in kilograms, right? Okay, so that many moles you have, right? So now you can put the value. You have an idea about the number of moles, you know the value of R, you know the temperature at standard temperature pressure 273, and you have the pressure which is 10 to the power 5. Everything you know, you can calculate the volume after that, right? Everything you know already, you can calculate the volume after that very, very easily, right? Okay, now let us move on and talk about the questions from the chapter of oscillation and waves, right? Now let us move on and talk about the questions from oscillation and waves, right? Which is going to be our part 2, right? Which is going to be our part 2. All right. All right. So just think about it. All right. So let's start talking about the second part, right? Which is oscillation and waves. Much simpler part compared to the thermal physics. It is much, much simpler. Okay. Lot more simpler than the previous part. Let us have a discussion of this idea. Okay. Let's see the first question. This is the first question. So question is giving you an equation. So x equals to 5 sine pi t plus pi by 3m represents the motion of a particle executing simple harmonic motion. The amplitude and time period of motion respectively are. So what will be the amplitude of motion? What will be the time period of motion? What will be the amplitude of motion? And what will be the time period of the motion? So this is asked in 2024. So the questions from this chapter are fairly easy. You see that? It is simply a format y equals to a sine omega t plus phi. Already if you just try to compare it, displacement is equals to a sine omega t plus phi, right? So you have to answer what is going to be the amplitude. So in place of amplitude you have 5, and now you have to talk about what will be the time period, right? What will be the time period? So time period is 2 pi upon frequency omega. Okay, so in place of omega you have pi, so 2 pi upon pi, so which is 2 seconds. All right, so amplitude is 5 meters and time period is 2 seconds. So 5 and 2 is the right answer. Option B is the correct option, right? I hope the idea is very, very clear. Right. Now let us talk about the next one. A simple pendulum is oscillating in the air, has a period of root 3 seconds. A simple pendulum is oscillating in the air and it has a period of root 3 seconds. If it is completely immersed in a non-viscous liquid, okay, it is immersed in a non-viscous liquid. So having the density 1/4 of the material of the bob, the new time period will be. So my dear kid, when you are going to immerse it in a liquid, so this is a pendulum. If the length of the pendulum is L, right, and the value of G over there is G, so the time period is going to be T is equal to 2 pi under root L upon G. Simple. But if you immerse it in a liquid, then what is going to happen? There will be buoyant forces on it. Due to the buoyant forces, the effective acceleration towards the gravity will reduce, right? So now the effective attraction towards the gravity, the acceleration towards the gravity has been reduced. So 2 pi under root L upon G, whatever the new value of G is there, right, that you have to use, right? So how will you figure out the new value of G? How will you figure out the new value of G? Huh? Think about it. Think about it. Let's try to discuss that. Okay. So what is the buoyant force? This is the thing. The bob is hanging over here in a liquid. So whatever is the weight of displaced fluid, that is how much buoyant force it will be experiencing, right? So the downward force is mg, the upward force is fb, buoyant force. The value of buoyant force is weight of displaced fluid, right? So we can say that mass of displaced fluid into density, mass of displaced fluid into g, right? Mass of displaced fluid is volume of displaced fluid into the density of displaced fluid, liquid, right, into g. Okay. Now volume of displaced fluid, Vd, is same as the volume of the bob, right? So that is same. Volume of displaced fluid is same as volume of the bob into rho L into g, right? Now the downward force is the weight, that is the volume of the bob into density of the bob, right, into g. Okay. So now if you subtract it, what is going to be the effective value of the net force? So the net force is going to be m into, let's say, g dash is going to be weight is this much, volume of bob into rho of bob into g, minus this part, buoyant force, which is volume of bob into density of liquid into g. All right, no problem. Mass of this m into g dash. So m is what? Mass of this bob, right? What is the effective acceleration? So this is volume of bob into density of bob, right? So let's call density of bob every time it is coming up. So density of bob, we can call it rho naught, right? So you see that from everywhere, volume of bob can be cancelled out, right? So g dash will be 1 upon rho. Rho bob is rho naught, basically, right? Every time writing. So this is rho naught into g minus rho L into g. So we can take the g as common, right? I'm just telling you the derivation of the formula. G as common upon rho naught minus rho L, right? Okay. So this is the idea that we have. G dash is g upon rho naught minus rho L, right? Or another way of writing that will be g dash is going to be g 1 minus rho L upon rho naught. Rho naught can be taken inside. So this is the effective value of g. So in many books this value is used directly. So now I have just given you a derivation that what is the effective value of acceleration due to gravity when it is hanging in the air. The acceleration due to gravity which is acting on the bob is g, right, which is 9.8 meter per second square. But once it is immersed in a liquid of density rho L, then the effective value of g dash is g into 1 minus rho L upon rho naught, right? So if you remember this much, you can directly apply it whenever you want, right? Okay. All right. So now once you know this idea, you can apply the same formula. Time period will be 2 pi under root L upon g dash. This is g dash, g minus 1 rho L upon rho, right? This is the value you can apply and you can get away with it. Okay. So I have already given you the concept. This is the concept over here. Okay. So over here we have it. The time period is equals to 2 pi under root L upon G effective. The effective value of G, this is the formula I have already derived, 3/4 of G that is coming out. So the ratio of time period will be, the actual time period is 2 pi under root L upon G, and the new time period is 2 pi under root L upon effective G, which is 3G by 4. So calculate the ratio, it comes out to be 2 seconds. Okay, the next question is the displacement of the particle executing SHM is given by this. Then what will be the amplitude of its oscillation, right? So what will be the amplitude of this oscillation? So basically, we have to talk about this particular part, right? Okay, we have to talk about this particular part. So here we have a question. We have a particle that is performing SHM, and the equation is A naught plus A sin omega t plus B cos omega t. So what will be the amplitude of this oscillation, right? What will be the amplitude of this oscillation? So we can clearly say that the equation is y is equals to this. This is the initial displacement. You can put it on this side. So y minus A naught is A sin omega t plus B cos omega t, right? Or take this thing as a whole and call it y dash is A sin omega t plus B cos omega t, right? Now you see what we do, right? Both the terms can be written in the cos term, so that we can replace them later, right? So here we have it. So the sin omega t can be written as pi by 2 minus omega t. So this is also same, A sin omega t plus B cos omega t. Just we have changed the format, right? And now if you try to write down the amplitude of this thing, so the amplitude of this thing is going to be under root A square plus B square, this square plus this square, plus 2ab cos pi by 2. Why is so? Because if you look at that, this particular displacement of the particle is coming as a combination of two different equations, right? Or you can think of this way, that this particle is there. For example, you may think of it this way. The assembly prayer happened in the morning, right? So sometimes there is a guy who performs the prayer and all the people, all the rest of the kids perform after him. Let's say that kid is not loud enough. So what will you do? What will teachers do during that particular prayer time? So they will take another kid, right, from the assembly, for the assembly purposes, and then he will also say the same stuff. So both the kids are saying the same prayer, right, and rest of the kids are reciting after them, right? So what is happening? Imagine a particle that is in front over here. So you see that one kid and the second kid over here, both the kids are sharing the same particles in front of them, right? Both the kids are sharing the same particles in front of them. So when both of them are going to recite the prayer for the rest of the students, so what is going to happen? The particles that were only oscillating initially by one kid are now getting energy from two kids, right? So one kid is providing this much plus B sin omega t. The amplitude of the first one was A, the amplitude of second one was B. So both of them are adding up to the amplitudes, and now the particle has this equation. This is coming from the first source, this is coming from the second source, which is why the equations of a particle executing SHM sometimes look like this, right? Because the energies are coming from two different sources, right? I hope it is making some sense, right? So A and B are clearly the amplitudes of individual sources, so provided by individual sources. So the net amplitude will be resultant of A and B. It is under root A square B square by 2ab cos pi by 2, which is the phase difference between them, right? So now you see that under root, that is coming out to be A square by B square. My dear kids, depending upon what is the phase difference between them, right, we can have different situations over here that we understand in the process of interference, but we are not discussing that much over here in one question. So over here we have it, the distance covered by a particle undergoing SHM in one time period is, so that is distance covered in one time period, right? So you see, in one time period particle will go here, the displacement covered is equals to amplitude for the maximum displacement, right? It is going to come back, so it will again cover A. It is going to go here for other side, again it will cover A, and again it will come back, so it will cover A again. So 4 times A it is going to cover in one full oscillation. Now look at this question, and we'll try to solve this one over here as well. So the radius of the circle, the time, the period of the revolution, initial position, and the sense of revolution are indicated in the figure. So everything is indicated in the figure. Okay, 3, 4. Okay, so everything is written over here. Y projection of the radius vector of rotating particle P is, what will be the Y projection over here? Y projection, right? Y projection of the radius vector. So this is the radius vector, right? The Y projection of the radius vector will be, so the radius is 3, right? The radius is 3, okay? All right. So rotating particle P is, the P is over here, okay? The P is over here. So the Y projection will be the entire thing. All right. So the Y projection will come out to be this thing, right? Which is coming from the extreme position at t is equals to 0. Okay. No worries about that. T is equals to 2, t is equals to 4 seconds. 4 seconds is the time period for this thing. Okay. Right. So you know that the equation is y is equals to a sine omega t plus phi, right? Okay. So the first part is for the amplitude. The first part is for the amplitude. The whole thing, the radius itself is 3 meters, right? So the amplitude cannot be more than 3. So automatically the option C is eliminated because this is over here. Okay. Now what is going to happen? All right. The amplitude over here, when it is in the first quadrant, the amplitude is positive, right? So this negative thing cannot be there. Okay. All right. Now it is 3 cos pi t by 2 and 3 cos 3 pi t by 2. So clearly 3 pi t by 2, this is not the displacement, right? The displacement in the first part is less than 90. So it would be this, right? The displacement omega is this much, right? So this, the angular frequency is this much. So 3 cos omega t, which is pi by 2 into t. That seems to be correct. So option, this one is correct, right? And how will you get that omega? Right? Omega can be this one and this one. How will you get that omega? So omega is 2 pi, t is equals to 2 pi by omega. So omega is 2 pi by t, na? So time period is given 4 seconds. So 2 pi upon 4 is pi by 2, right? So pi by 2 is written over here. This is omega. So A is given, right? And omega is given. Simple. A sine, A cos omega t. A cos omega t. Radius was 3, so A is 3. Omega is pi by 2 into 3. I hope the idea is very, very clear. The xt graph of a particle performing SHM is shown in the figure. The acceleration of the particle at t is equals to 2 seconds is going to be, right? So very simple kind of numerical it was, right? Now you need to tell that what will be the acceleration of the particle at t is equals to 2. So at t is equals to 2, the particle is at the mean position. Acceleration would be maximum. Acceleration at this position is going to be a omega square. You know that, right? Acceleration is a omega square into y. So here we are at the maximum, maximum displacement, right? Maximum displacement, amplitude position. So that is why the displacement is equals to y, right? So displacement over here is 1 meters, right? Okay. And negative, positive signs are also coming up. So negative sign tells us that the acceleration, the nature of acceleration is always opposite to the nature of displacement. You see, when the particle is moving this way, the acceleration, the restoring acceleration of the particle is in the opposite way. So this negative sign tells that. So omega square into y, y over here is equals to displacement. So displacement over here is how much? 1, 1, 1. Omega square. So omega is, here you have the time period. So in the entire cycle, the time taken is 8 seconds. So omega is going to be 2 pi upon time. Omega is 2 pi by t. T is 8 seconds. So that is alpha for you. Pi square by 4 square minus pi square by 16. All right. So option A is the option B is the correct option, right? Option B is the correct option. I hope the idea is very, very clear, right? The phase difference between the displacement and acceleration of a particle in SHM is, what is the phase difference between the displacement and the acceleration? What is the phase difference between displacement and the acceleration? So my dear kids, the displacement of a particle performing SHM is y is equals to a sin omega t. What is the equation for acceleration? So first you get the differentiation, get the equation for velocity. It is a cos omega t, ra? A cos omega t, and differentiate omega again. So a omega cos omega t. Differentiate velocity, you will get acceleration. So a omega square cos omega t is minus sin omega t. All right. So how will you put these two things in perspective? So sin omega t and minus sin omega t. So clearly we can say that it is sin omega t plus pi. So that will come out in third quadrant, and minus sign can be taken inside. So here we have it, y and a, the displacement is in first quadrant, then the displacement is acceleration would be in third quadrant. So the phase difference between them come out to be pi radian, right? A particle executing SHM with amplitude a has the same potential and kinetic energy and the displacement. So what will be a particle executing SHM with amplitude a has that same potential and kinetic energies at the displacement. Acha. So at what values of displacement you will have the same potential and kinetic energies? At what value you will have same potential and kinetic energy? So let us say that displacement is x, right? This is the original position, x equals to 0. So at a displacement x from the mean position, let us say that the kinetic energy and the potential energy is same, right? Okay. So what is the kinetic energy at this place? It is half mv square, right? So half, we can say that m and m will cancel out. So v is k under root this. So under root will remove because we have v square. So v is a square minus x square, right? This should be the value of kinetic energy, right? Half k a square minus x square. What will be the potential energy, right? So the potential energy is going to be half k x square, right? At a displacement x, the potential energy is half k x square. So k, this part can be removed. So a square minus x square is same as x square. 2x square is a square. So x square is a by 2, a square by 2. So x is a upon root 2. So at that value of displacement, we have same kinetic energy and potential energy, right? Which is option C. All right. So we have two identical point masses P and Q, and these 2 point masses are suspended from 2 separate massless springs of spring constant K1, K2 respectively oscillate vertically in their maximum speeds are same. If their maximum speeds are same, the ratio of amplitude of AQ of the mass Q to the amplitude AP of mass P is going to be. So my dear kids, they are oscillating vertically, and if their maximum speeds are same, they are already giving us that the maximum speed of these particles are same. So my dear kids, what is the maximum speed? It is omega into a, right? Maximum speed is omega into a, right? And that is same for both of them. All right. What is omega? It is under root k upon m. Huh? All right. So that is going to be same. So let's equate them and then solve it. So let's see. Okay. So omega is under root k upon m. We know that for a spring oscillating spring pendulum, omega is under root k upon m. Maximum velocity is omega into a. So omega is under root k by m. So for the first spring, it is k1 upon m. And for the second spring, it is k2 upon m. And they are giving us that the maximum velocities are same. So we will equate them. This will cancel out, right? And it will give us the ratio of their amplitude is this under root k1 by k2. Right, the displacement of the particle traveling wave is this, where t is time, x is distance, lambda is the wavelength, all in SI unit. What will the frequency of the wave? Right, my dear kids, what will be the frequency of the wave? The question is giving y is equal to c sine 2 pi by lambda into at minus x, right? 2 pi by lambda into at minus x, right? So if you try to compare it with the standard equation of a traveling wave, y is equal to a sine omega t minus kx, right? If you try to compare it, y is equals to a sine omega t minus kx. So you see that the value of k here is 1. Omega is, no, not 1. This 2 pi by lambda can go inside. So value of k will come out to be 2 pi by lambda. Value of omega will be 2 pi by lambda into a, right? So those things we have over here. So this 2 pi by lambda needs to go inside, because you see that we need this format. A sine, nothing is here, omega t minus kx. We have this thing now. So the equation it should be y is equals to c sine 2 pi by lambda at minus 2 pi by lambda into x. Now we can further solve it. Right. Now we can further solve it. So from these equations, the omega and everything can be figured out, right? Just by comparing. In place of omega, we have that. In place of this, so omega is equals to 2 pi into v. So just comparing it, we will a upon lambda. So the initial tension on a stressed string is doubled, then the ratio of the initial and final speed of a transverse wave along the string is going to be. So what will be the, if that is doubled, then what will be the ratio of initial and final speed traveling around the transverse wave? So my dear kids, for a string wave, the velocity of a wave traveling through a string is under root tension upon, mass per unit length, under root t upon mass per unit length, right? So you see that if there is no tension in the string, the wave cannot travel in it, right? So both the situations are there, just the tension is doubled, so two cases can be formed, and then we'll equate it, right? So here we have it. So velocity is of a wave is under root t by mu, right, mass per unit length. And here if the tension is doubled, the velocity will change. So if you just take the ratio and you can solve it, right, v upon v dash is 1 upon root 2, that's it. The fourth overtone of a closed organ pipe is same as the third overtone of, just a second. Fourth overtone of closed organ pipe is same as third overtone of open pipe. Okay. Fourth overtone of a closed organ pipe is same as third overtone of an open pipe. The ratio of the length of closed organ pipe to the length of open pipe is going to be, what will be the ratios of their length? Right. This is what we have to figure out. Right. So fourth overtone of a closed organ pipe, it is fourth overtone of a closed organ pipe. For a closed organ pipe, the fourth overtone will be 9 times of original value, right? 9 times of V naught, right? Okay, 9 times of original fundamental frequency, right? Whatever that fundamental frequency is. And the third overtone of open pipe, is 4 times of fundamental frequency, right? 4 times of fundamental frequency. They are same. We will equate them. So 9 times fundamental frequency of the closed organ pipe is coming out to be same as third overtone. Third overtone is 4 times fundamental frequency. That needs to be same, right? Make sure you put the correct values. So yeah. Okay, so fourth overtone of closed organ pipe is 9 times nu naught, which is V upon fundamental frequency of closed organ pipe is V upon 4L. You know that, right? And third overtone of closed organ pipe is open organ pipe is 4 times nu naught, and the fundamental frequency of the open organ pipe is V upon 2L dash, right? So yeah, we can further just equate them. Length of the open pipe and length of the closed pipe we have imagined, right? So we just equate them, and by equating them we will get the value L upon L dash, which is 9 by 8. Okay. The ratio of frequencies of fundamental harmonic produced by the open pipe to that of closed pipe having the same length is, come on. So we have just given you the formulas, right? The fundamental frequency for the open organ pipe is going to be nu upon 2L naught. All right, yes or no? And for the V upon 2L naught, right? And for the closed organ pipe to that of closed organ pipe, open organ pipe to that of closed organ pipe, it is V upon 4L naught. For closed organ pipe, it is V upon 4L naught, right? Okay. So once you know all these values, L naught, here if we have assumed because they are not telling us the length of these organ pipes, so let's say that the length we have assuming are different. It is for the organ pipe and this is for the closed pipe, right? Because they are not telling us the length of individual pipes, so this is the same. Now we have to take the ratio for the same length. LO and LC are same, so we have to just take the ratio we can simplify it, right? We can just take the ratio and simplify it. So, okay, this is for the open pipe, this is for the closed pipe. We take the ratio, it will cancel out, it will come out to be 2:1, right? Now, the tuning fork with frequency 800 Hz produces a resonance with resonance column tube with upper end open and lower end closed. So, it's a closed organ pipe, right? Okay, so now what is happening? Successive resonance are observed at length 9.75 and 31.25 and 52.75. The speed of the sound in the air is, because we get the successive resonance in these things, that means if I take the difference in the length of the air columns successively, it will be equals to lambda by 2, because at open end you will have always antinode will forming up, and at the close end where the water is, a node will be forming up, right? So always the length will come out to be lambda by 2. So there are different situations where you get the separation as lambda by 2, right? And the frequency is already written as 800 hertz, right? So what will really happen? Once you know that lambda by 2 is the difference of these values, right? The lambda by 2 is difference of these values, right? And once you know that, that will help you to figure out the value of wavelength, right? Lambda of wavelength traveling in the open organ pipe. Once you know the wavelength and you also know the frequency, you know the wavelength and frequency, you can get the velocity, right? V is equals to nu into lambda, right? So speed of the sound in air column we can figure out, right? You see that L3 minus L2 or L2 minus L1 is L1 by 2, right? You see that you take the difference 9.25 and 31.25, right? So around 21, and 52 minus 31 around 21. So that difference is coming out to be 21.5, right? So the difference of length, successive length, is always lambda by 2, which is 21.5, right? So lambda will be the wavelength traveling will be double of that, 43, right? Okay, so once you know the wavelength of wave traveling in the open organ pipe, right, of this tube, so V is equals to frequency into wavelength. Frequency is already given 800 hertz. Lambda we have calculated 43 centimeter, convert into meters, right? So just answer it will be 344 meter per second, and that is the correct answer, right? So I hope the idea is very clear, right? That was pretty much everything about these chapter. Around 50 questions we have solved from the chapters of thermal physics and from the chapter of waves, right? So I'll keep this lecture till here only, right? Keep on learning, and I'll see you there in the next class. Till then, take care. Bye bye.